Welcome to our module on machine learning for business analytics, a crucial topic today. Our focus will be on empowering data-driven decisions and extracting valuable insights from your data. Let's begin by addressing the fundamental question. What exactly is machine learning? At its core, it's about systems learning from data to continuously improve their performance. Let's first look at the core definition of machine learning to establish a foundational understanding. Well, machine learning is an important field within artificial intelligence, or AI as we often call it. It enables computers to learn directly from provided data, rather than being explicitly programmed for every task. This learning allows systems to improve their performance over time, without needing constant, explicit programming updates. Now, let's consider the significant business value that machine learning brings to the table. It empowers businesses to make more informed, data-driven decisions, moving beyond mere intuition. Machine learning excels at detecting complex patterns and hidden trends within vast amounts of data. Ultimately, it helps us derive valuable and actionable insights from all our historical business data. We will now explore the fundamental differences between supervised and unsupervised learning approaches. These distinct approaches are chosen based on the type of data available and our specific learning goals. Let's compare these two learning paradigms across several key aspects to understand their differences. First, we consider the type of data required for each learning approach. Next, we look at the typical output generated by models from each category. Then, we define the primary learning goal that each method aims to achieve. Finally, we'll examine some practical use cases where each learning type is commonly applied. Let's start by detailing the characteristics of supervised learning, a widely used method. Supervised learning uses labeled data, meaning each input has a corresponding known output. The output of a supervised model is usually predicted, labels for classification, or continuous values for regression. The goal is to learn a function that accurately maps input features to their correct output labels. Common use cases include identifying spam emails and predicting stock prices based on historical data. Now, let's turn our attention to unsupervised learning and its unique characteristics. Unsupervised learning works with unlabeled data, where only input features are available without predefined outputs. Its output involves discovering inherent groupings or associations within the data itself. The main goal is to discover hidden patterns, structures, and relationships within the unlabeled data. Examples include customer segmentation for targeted marketing and anomaly detection to spot unusual activities. Let's delve deeper into the two primary types of supervised learning algorithms. Both types focus on predicting specific outcomes by learning from pre-labeled training data. First, we have classification, which aims to predict a categorical outcome or label. For example, it can predict if an email is spam or not spam, assigning it to a specific category. Next, there is regression, which focuses on predicting a continuous numerical value. This could involve forecasting sales revenue, where the output is a continuous number. Now, let's explore the various types of unsupervised learning techniques available. These methods are all about discovering inherent structures and patterns within unlabeled datasets. Clustering is a key technique that involves grouping similar data points together into distinct clusters. This process helps us identify natural groupings within our data, such as customer segments. Association rule learning helps us find interesting relationships and dependencies between variables. This is often used to discover which products are frequently purchased together. For instance, dimensionality reduction aims to simplify data by reducing the number of features. It achieves this while still preserving the most important characteristics and information of the data. Let's outline the 5 key steps involved in successfully performing customer segmentation. The first step involves gathering relevant customer data and preparing it for analysis. Next, we select the most appropriate clustering algorithm based on our data and goals. Then, we train our chosen clustering model using the pre-processed customer data. After training, we evaluate the model's performance and interpret the resulting customer segments. Finally, we apply these insights to develop and refine our overall business strategies. Now, let's explore some of the key clustering techniques commonly used in practice. These methods provide different ways to effectively group our customer data based on similarities. First, we have k-means clustering, a very popular and straightforward algorithm. It partitions data into a predefined number of k clusters, where k is a chosen integer value. The algorithm works by minimizing the variance of data points within each individual cluster. K-means is known for being simple, fast, and efficient, especially when dealing with large data sets. Next, we'll look at hierarchical clustering, which builds a tree-like structure of clusters. This method constructs a nested hierarchy of clusters, often visualized as a dendrogram. It either merges similar clusters or splits larger ones based on their data point similarities. A key advantage is that it does not require you to specify the number of clusters beforehand. DBSCAN is a density-based algorithm effective for discovering clusters of varying shapes. It identifies clusters as areas of high density, grouping together closely packed data points. This algorithm is good at handling clusters of arbitrary shapes and identifying noise or outliers. However, it requires careful selection of its parameters, epsilon and minimum points, for optimal results. Finally, we have Gaussian mixture models, or GMM, a more probabilistic approach. GMM assumes that our data points are generated from a mixture of several Gaussian distributions. It assigns probabilities to each data point, indicating its likelihood of belonging to each cluster. This allows for soft clustering, meaning data points can potentially belong to multiple clusters simultaneously. Let's now explore the core principles behind how decision trees operate. Understanding this tree-like model helps us grasp how decisions are systematically made. The process begins at the root node, which represents the entire dataset under consideration. This initial node holds all the data before any splits or decisions are made. Next, the data is split into multiple branches based on a specific feature or condition. This splitting process aims to create more homogeneous subsets of data in each branch. This splitting process then repeats recursively on the newly formed branches. It continues until the data in each node becomes sufficiently homogeneous or a stopping criterion is met. Finally, we reach the leaf nodes, which represent the ultimate outcome or decision. These leaf nodes provide the final prediction, such as a class label for classification tasks. Let's now explore random forests, which harness the power of ensemble learning. By combining multiple decision trees, random forests provide highly robust and accurate predictions. Bootstrapping is a key technique where multiple decision trees are built from random data subsets. This process involves sampling with replacement to create diverse training sets for each tree. Bootstrapping is crucial for reducing the common problem of overfitting in individual decision trees. Feature randomness further enhances diversity by considering only a random subset of features. For every split in a tree, only a random selection of features is evaluated, not all of them. This randomness ensures that individual trees are distinct, leading to a more robust overall model. The final prediction is determined through a process of voting or averaging across all trees. For classification tasks, the class predicted by the majority of trees is chosen as the final output. In regression problems, the final prediction is obtained by averaging the outputs from all individual trees. Let's break down how sentiment analysis typically works step by step. We'll cover the essential steps required to extract valuable insights from various text data sources. The first major task involves collecting the raw text data and preparing it for analysis. This means gathering raw text from diverse sources like reviews, social media, and forums. We collect data from customer reviews, social media posts, and other relevant textual sources. This often involves using web scraping tools or accessing platform APIs to retrieve the text. Once collected, the text must be pre-processed to clean and standardize it for analysis. This includes tokenizing the text, breaking it down into individual words or meaningful phrases. We also remove common stop words and perform stemming or lemmatization to normalize words. The next major task is to determine the sentiment expressed within the processed text. This involves classifying the sentiment into predefined categories, such as positive or negative. Machine learning models like naive Bayes or SVM are often used to classify sentiment categories. The text is then classified as either positive, negative, or neutral, indicating its emotional tone. Beyond classification, we can also assign numerical sentiment scores to quantify intensity. For instance, a score of -1 might indicate negative sentiment, while +1 denotes positive. This step also helps identify sentiment around specific aspects or features mentioned in the text. Let's discuss the numerous benefits of leveraging AI for business decision making. AI has the power to fundamentally transform both daily business operations and long-term strategy. One major benefit is the significant increase in speed and overall efficiency. AI systems can process immense volumes of data at a speed impossible for humans. This leads to quicker decisions that can be implemented effectively across an entire organization. Another crucial advantage is the greatly enhanced accuracy of decisions. AI helps reduce the likelihood of human errors, leading to more reliable outcomes. It also excels at uncovering subtle, hidden patterns in data that humans often miss. Significant cost reduction is also a compelling benefit of AI integration. I can automate many routine and repetitive tasks, freeing up human resources. This automation helps to optimize various business operations, leading to greater efficiency. Finally, AI offers impressive scalability and continuous learning capabilities. AI systems can easily handle growing data volumes and increasing complexity without issue. They also continuously learn and improve their decision-making abilities with new data over time. To conclude, let's recap the key takeaways from our discussion today. These are the essential points to remember about machine learning for business analytics. Remember, machine learning, or ML, empowers data-driven decisions and helps detect complex patterns. Supervised learning uses labeled data for predictions, while unsupervised learning discovers patterns. Clustering is vital for segmenting customers into groups, enabling personalized business strategies. Decision trees are interpretable, whereas random forests offer more robust and accurate predictions. Sentiment analysis extracts customer emotions from text, providing valuable marketing insights. AI transforms business decisions by offering enhanced speed, accuracy, and scalability.